Good day and welcome to this presentation on feedback. Before I really start, I want to make some introductory remarks first. And I'd like to pay my thanks to Chris Rutgers of Habitat Design Audio for recording this presentation, editing it, releasing it, etc. Without him, this would not materialize. My name is Hans van Manen. I'm a physicist by training, with knowledge of both mechanics and electronics. I'm a great music lover, but I don't want to hear my system. So for my background, I have a different view on, through the years, how to develop music reproduction which is perceptual better. I'm head of development of temporal coherence, and where I use my view as a physicist and with the way that I think it should be done to design our equipment, which in general achieve perceptual good result in the products. And hopefully it will become clear during the presentation. The presentation itself is sizable, but it's possible to view it in parts. My advice is when the contents are unfamiliar or experience is difficult, please split it into different parts, and you can even review part again before continuing. So I've indicated the 4 parts with different colors of the contents, but they will be announced after each section, so you can know where to really come to. I try to avoid mathematics in the presentation as much as possible. Only a few times a few simple equations show up. And if you don't believe me on my blue eyes, you can find the mathematical underpinning in a number of publications on our website. The contents, the first section is about the problem description, the quality assessment of audio equipment, the findings of other authors, Fourier theory, background, requirements and conditions, a basic cognitive flow in the common feedback theory. The second is about the interactions between the limitations of amplifiers and the consequences. Interaction of distortion and bandwidth limitation as a nice example of these kind of interactions, and amplifiers with multiple amplification stages. Then we do the calculations of dynamic response and the artifact generation that we've come across, and we look at other sources of non-ideal behavior which are perceptual, and the load with a loudspeaker versus a resistor for the amplifier. And we look at artifacts which cannot be detected with continuous sine waves, the basic of the common approach. Well, from the whole thing we have some findings on and learning points about regarding feedback, and you can find directive for the assessment and the design of amplifiers. And finally we come to some conclusions. Well, the first part will be about problem description, quality determination, literature findings, and error in the feedback theory. There's a strong difference of opinion on feedback. Some people say you cannot have enough feedback, whereas others state that you should have electronics without feedback because a feedback amplifier does not sound musical. Of course, both views are completely incompatible, but why are these so different? And on which results are they based to come to such conflicting opinions, and on which properties should be focused and can be used to improve the electronics perceptually? I'm not interested in what a meter tells me, I'm interested in what my ears tell me. As an example that feedback can be used for good results, we can mention professional disc cutting machines. There's not a single one which does not use without feedback. So relentless banning feedback does not look wise, or in other words, put it with garbage, does not look wise thing to do. But does more also mean better? First of all, we have to formulate criteria to determine the perceived quality of electronics to verify these with different experiences and observations. How is this usually done? Well, the standard techniques for assessing the quality of electronics are amplitude response with frequency using a resistive load, phase response with frequency, sometimes square wave response, sometimes intermodulation, sometimes, but it's becoming more and more rare. Tone burst response, rarely. Maximum power in the resistive load, okay, that's a standard thing with specifications, so that's done. The properties with complex impedance, what that's B will come back in a minute, but it's virtually never done. Distortion, sometimes as a function of the delivered power to a resistive load at 1 kilohertz, and of course the perceptual assessment. The question is this sufficient? Well, the amplitude response frequency is usually not a problem for a modern semiconductor amplifier. Perceptual assessment, on the other hand, is often looked at as subjective and thus as unreliable. Consequently, most look at the distortion figures with a resistive load, and these are, say, less than 0.01% for a modern good amplifier in most cases. So are these figures useful? Well, distortion figures of amplifiers are orders of magnitude smaller than those of loudspeakers. If you have a good loudspeaker, well, 0.5, then you have a very good one, but say 1% is pretty common. So that's 100 times more than the 0.01% of the amplifier. And still differences between the amplifiers can easily be discerned by listening to them with loudspeakers which have 100 times more distortion. And I have an example which is not real amplifiers, but it was electronic equipment, and they had extremely small distortion figures. I better expect it in parts per million than in percent. It was 8 ppm versus 10 ppm, the same brand, but at the first notes you could hear a clear difference in the perceived quality. And on the other hand, many high-end lovers prefer vacuum tube amplifiers or semiconductor amplifiers, even though the distortion figures of the latter are far superior than of those vacuum tube amplifiers. And in that respect, it's interesting to cite a paper that was presented at the Audio Engineering Society convention in Munich, May 2009. It was a Polish professor, and he had a presentation which the subjective and objective evaluation of 5 high-quality amplifiers, vacuum tubes, were presented, and the reference was a professional transistor amplifiers, and you may assume that a professional amplifier has very good specifications. The subjective evaluation was done by a team of judges and evaluated with the use of a psychoacoustic model, and it was found that the best sound quality is obtained by the vacuum tube amplifiers, the worst by the reference amplifier. The results of subjective evaluation are inconsistent with quality assessed by measurements of objective parameters. All amplifiers have comparable quality, but the best is the transistor amplifier because of the lowest level of total harmonic distortion or noise. Dr. Arttu Kulinemi, a Finnish guy, brought out a book which is basically a more popular version of his PhD thesis, and I'll cite some of his statements. And this one's the first one. Many transistor amplifiers produce so little harmonic distortion that it's unlikely that it would be the reason for subjective differences between units. This leads to the conclusion that there must be other error sources than those that are usually analyzed, which have a major effect on audible quality. So it brings us to an important statement, because both authors note that there is a certainly perceived difference between amplifier and audio amplifiers which are audible with loudspeakers, but that the perceptual quality assessment is not consistent with the result of the commonly used measurements. And some people then conclude that the perceptual assessment is therefore unreliable. Distortion measurements are done with a resistive load, but the loudspeaker usually has a complex impedance, and I mean with this. This is an example of a loudspeaker measured by a stereophile, and the drawn line is the modulus of the impedance, and you have to use a left-hand scale, and it varies between, say, a little over 3 ohms to almost 15 ohms, so it's a factor of 5. But the phase, and you have to use this scale for it, varies between, by the dotted line, between, say, -30 to +45 degrees. And because the phase is not zero, the impedance is called complex, because you have to describe it by the complex numbers. But it means that there is a voltage shift in phase between the current and the voltage. Because a resistor would have one single value, say 8 ohms, and one phase 0 ohms. Well, this is quite different. And can this lead to perceived differences? We'll come back to this later because it's at this moment not illegal. But actually, when you think about it, it's incomprehensible that after 130 years of sound reproduction, we still don't have a measurement technique which is able to predict the perceived quality of audio equipment. Okay, we'll come back to Mr. Cognummi. And one understatement is that most amplifiers today rely on high global negative feedback. When loop gain is high enough, input circuitry operates at low signal levels, allowing very simple circuits to be used without compromising linearity. This assumption is valid when operating is analyzed using a single tone and steady state input signals. However, it is possible that this design philosophy results in amplifiers with poor dynamic, transient and overload recovery performance. Another is that poor dynamic properties cannot be understood from the evaluation of amplifiers and systems by single tone analysis, which are based on Fourier theory. So we must be overlooking some essential points. But which ones? Could these be related to those other error sources? Wow, this is quite a statement. It means that the common analysis based on the Fourier theory does not provide consistent results for the dynamic response of electronics. And on top of this, structural differences can be discerned when the response from 20 Hz to 20 kHz is identical, but differs above it. This became clear with the reconstruction filters of CD players, because it does make difference in how it behaves above 20 kHz for the perceptual evaluation. So is this theory flaw, or is there another reason? Anyway, we conclude that the amplitude response with frequency in combination with distortion figures still next to useless for the prediction of perceived quality of electronics. But then, what is useful? Well, Cognummi points in a number of remarks to the difference between responsive amplifiers to continuous sine waves with a fixed amplitude and their dynamic response. The latter is rarely studied, but music is, of course, dynamic. A continuous sine wave is not. What causes the differences? Can we determine these and subsequently relate it to the perceived differences between amplifiers? Well, first we'll have a quick look at the background why this testing with continuous sine waves is usually done. Why is this frequency response so important? It's based on the Fourier theory. And cutting many corners, it states that if I know the response for continuous sine waves, I know how it will respond to any signal, including music, which is built up from these waves and frequencies. Human hearing reacts to waves of 20 Hz to 20 kHz, so it states that the response of a system over this range fully determines how our hearing experience the sound. It has been one of the major pillars or cornerstones of audio analysis for decades. But the theory on which the common analysis is based is mathematically completely sound. There is nothing wrong with it. This was developed mostly during the 19th century, and it's a very elegant piece of mathematics, I can tell you, because it was taught me as well. But Monsieur Fourier would turn in his grave if he knew how important, and it's very diplomatically put, the theory is applied and used nowadays. The reason why is that it's often overlooked or swept under the carpet. The application of the theory is only allowed when the boundary conditions are fulfilled. And two very important, not the only ones, but two very important ones are that such systems need to be linear and time invariant. Linear means that if an input signal, e.g., becomes twice as large, the response should also, in all aspects, become exactly twice as large. Time invariant means that all properties of the system do not change with time. And to give a simple example of which is not correct, a resistor which warms due to the current which is flowing through it and warms up and thus acquires different resistance is not time invariant. Electronics, like amplifiers, are neither linear nor time invariant. If an amplifier would be linear, it would not distort, and therefore the whole issue of feedback would not be non-existent. And due to all kinds of memory effects, an amplifier is not time invariant, and we'll show that later in more detail. And the power supply of an amplifier may only be regarded as time invariant under strict conditions. And that is rarely the case, and that has also become clear later on. So as a consequence, the Fourier theory may in general not be applied to electronics. It's inconvenient, so this band is swept under the carpet for simplicity reasons, but don't be surprised that you will get incorrect results, if not just nonsense. The boundary conditions for the applications of the theory are not imposed without a reason. Note that the system should also be linear internally. So don't say, well, due to the feedback my system is virtually linear, so I may use it. No, internally it's not linear. So if that's not the case, then you're not allowed to apply the theory. Human hearing is also non-linear and not time invariant, which is the main reason why we hear in time. So what are the consequences of this all? Well, they're quite a lot. But before we can go into more detailed discussion, we have to go through a number of conceptions before we can discuss this. So these are the ones. There's a short list of things we need. There are a lot more, but these ones we need. First order filter is a frequency-dependent network having a slope of 6 dB per octave. And the second order filter is the same, but then having a slope of 12 dB per octave. And for those who can calculate by head, they understand that 12 divided by 6 is 2, which explains first and second order. Then we have direct current voltage. That means very low frequencies will indicate it with DC, which is the shorthand for direct current. And alternating current voltage of all frequency is indicated with AC. And signals far above the upper limit of hearing, let's say above 75 kilohertz, but it's just very high. We call high frequencies, and we'll use HF for that. Then we have the open loop amplification. That's the amplification of the amplifier without feedback. And symbol is mu. Then we have the open loop amplification at DC, and that's indicated by mu0. The closed loop amplification is the amplification with feedback. And the feedback fraction is the part of the output signal which is returned to the input, and symbol beta. And the feedback factor is the product of mu and beta, and the symbol is mu beta. Well, there's a cognitive flow in the well-known feedback theory. The derivation of the well-known equations for amplifier is feedback is relatively simple. High school mathematics should do the trick. A closer look learns that much misery is reduced by the factor mu0 beta. So the closed loop bandwidth increases with that factor, the distortion is reduced by that factor, the output impedance is reduced by that factor, etc. Seems like an ideal way to improve the quality of an amplifier, a kind of miracle cure. But a crucial cognitive flaw has crept into the derivations, because the starting point of the calculations at mu0, the open loop gain, is a constant. The derivations of the equation is done per parameter. We keep everything perfect except for one. So we'll just look at the distortion, and we keep the bandwidth infinite, and we'll keep the output impedance infinite, 0, etc. And then we'll calculate what happens to the distortion. But it will only work, of course, if you have or, but in reality it's and. I have distortion, I have a limited bandwidth, I have a non-zero output impedance, etc. So, means that the interactions of these things are completely incorrectly set under the carpet. So you get interactions, but they are not that easy to grasp, I have to admit. So I will illustrate that by looking at two important limitations of amplifiers, being the nonlinear distortion and the bandwidth limitation, and how these interact. First, the background of both will be elucidated, and then we'll look at the consequences of the mutual interactions. This ends part 1.